Hello, my name is Matthew Johnson, and today we're going to talk about interdependence analysis. In the last video, we introduced Coactive Design, which is about designing support for interdependence in human-robot teamwork. Today, we're going to introduce a tool called the Interdependence Analysis table that helps us do that. For a more detailed explanation of Coactive Design, please check out my video on that topic. But as a quick review, Coactive Design is about designing human-robot systems that support interdependence. It highlights three capabilities that are needed for effective human-robot teamwork, specifically observability, predictability, and directability. It also suggests that the greater individual competence of a given technology, there'll be a need for a matching sophistication and collaborative skills. Yogi Berra is often credited with saying, in theory, there's no difference between theory and practice. In practice, there is. Today's discussion is about how to ground out theory presented in the Coactive Design video into practice. Given Coactive Design's focus on interdependence, there are some important questions designers need to answer, like how do you identify interdependence in a system? How do you identify the potential need to support interdependence in a system? How do you characterize a requirement that meets a need to support interdependence in that system? The answer is performing interdependence analysis. This is an approach at the heart of Coactive Design that helps bridge theory into practice. So let's dive in. To help conduct interdependence analysis, or IA, we have developed a tool called the Interdependence Analysis table. The IA table has three main parts. The first section is a model of the work, or as we would say, the joint activity. I have a different video that covers joint activity and teamwork, but for now, thinking of it as the work will suffice. The second section is where we identify and assess the potential interdependencies. This is where the actual analysis takes place. The third section is used to analyze the potential workflow supported or not by the interdependence. This section connects the formative design to the physical design and enables grounding out the theory directly into specific system components. Section 3 will be covered in a different video. Here we're going to focus on sections 1 and 2. These two sections usually provide sufficient answers to our original questions and enable designers to identify potential interdependencies, identify the support needed for a particular interdependence, and characterize requirements that meet those needs. So back to the first section. This section is where you develop a simple hierarchical model of work. Traditional engineering might use hierarchical task analysis, but a more appropriate choice would be a cognitive task analysis or goal-directed task analysis or something similar. The end goal is a simple hierarchical representation of work. Regardless of your choice of model, you should identify the knowledge, skills, and abilities, both physical and cognitive, required to do the work. For example, when considering the work of opening a door, you need to not only consider turning the knob and pulling, physical actions, but also how you would determine where the knob is, sensing, and how you knew where to stand to reach the knob, understanding. It's crucial to include cognitive aspects since this is often where the interdependence can be found. Lastly, the model should be captured in an agent-neutral manner, meaning only consider the work and not the worker. That comes later. For example, you should model turning the knob and pulling because all agents would need to do these functions to operate the door. But you should not model something like open gripper for the work of opening a door because not all agents have grippers. Thinking about things in an agent-neutral way can be tricky for some people, but it becomes easier with practice. On to section 2. This section is where we identify and assess the potential interdependencies. This is where the actual interdependence analysis takes place. In the Coactive Design tutorial, I discussed how interdependence is not about functions, it's about relationships between agents. Section 1 captures the work context, but we need to capture the team context to understand interdependence. Section 2 enumerates the teaming alternatives. You need to have some idea of the team doing the work to be able to consider how they might or might not be interdependent. The more you know about the team, the better, but you can generally get by with the generalization of roles or types. This example shows 4 potential team members, agents A, B, C, and D. Most examples in this video are single human, single robot for simplicity, but interdependence analysis can support larger team analysis, and there will be an example showing how to do this a little later on. Once we've enumerated the team members, we then assign one team member as the primary performer and assess their capacity to perform the work. The performer, in this instance Agent A, is listed in the performer column labeled P. To assess the performer's capacity, we use a fairly broad categorization captured by a color coding scheme. Under the performer column, green indicates that the performer can do it all, very reliably. Yellow indicates that they can do the task, but their reliability is less than 100%. Orange indicates that they can contribute to the task but need assistance. For example, you may not be able to lift the entire table, but you could help lift the table. And red means you can't do anything to help with this particular aspect of the work. This categorization provides a general characterization of the performer's ability to do the work and also where the performer might need help from a teammate. Yellow and orange indicate brittleness in their work, and red indicates a lacking capability. After assessing the performer, we then move on to assessing the supporting team members. Here we have 3 teammates, B, C, and D, and they're listed under the supporting header. Similar to the performer assessment, we use a broad categorization captured by a color coding scheme. However, instead of assessing the ability to do the work, we assess the ability to support another doing the work, and this is a little bit different. The color coding scheme now means something slightly different. This changes the meaning of the color coding scheme. For these columns, green is used to indicate that your assistance could improve efficiency. Yellow is indicating that your assistance could improve reliability. Orange is indicating that your assistance is required, and red is indicating that you cannot provide any assistance. This categorization provides a characterization of the supporter's ability to provide help. Orange indicates a hard interdependence. Green and yellow indicate soft interdependencies. Red indicates that there is no potential for supportive interdependence. The overall color coding pattern provides insight into when and where help is needed, when it is possible, who can potentially provide it, and how well. Thus, it answers the first 2 of our original questions and enables designers to identify potential interdependencies and identify the support needed for a particular interdependence. Next, we consider another team member as the primary performer and repeat the process. Each alternative will likely be different due to differences in performers' capabilities and supporters' potential to assist, resulting in different potential interdependencies. Ideally, you should permutate through all team members as performer to understand the potential interdependencies. This seems daunting, but in practice there tend to be patterns that emerge that reduce the scope of this permutation, but that's a discussion for a future video. The last step is to derive the requirements. These interdependence pairings can be used to derive observability, predictability, and directability requirements, and this answers the third of our original questions and enables designers to characterize requirements that meet the interdependence needs. So those are the basic steps. IA can be challenging at first and take some practice, so to help develop your understanding, we will walk through a few examples. We will start with a simple example from Terry Fong's collaborative control thesis. It involves the task of remotely assisting a robot with navigation. We begin with a simple model of the work, which would be navigation that involves avoiding obstacles, which involves sensing obstacles, interpreting them as passable, and deciding to proceed or divert. Next, we add the teaming alternatives. In this case, we have 1. The task is to drive around, and the robot is the only member that can do that. The only role the human can play is the supporting one. So in this case, there is no need to permutate alternatives. This is a bit unusual, but a nice simplification for our first attempt. Next, we assess the performer, in this case the robot's capability. We see it can do everything reliably except interpret obstacles, which is yellow. The yellow indicates the brittleness in the robot's ability to interpret obstacles. In other words, it's less than 100% reliable. This is what Fong was trying to address through collaboration with a human. Next, we assess the human's ability to support. The human can interpret obstacles, but it also has some limitations. In other words, it's possible that the human could incorrectly interpret an obstacle as well, so it's also yellow. The human also cannot assess the performer, or the robot's, uncertainty about its own interpretation of obstacles. This will come into play later. The yellow under the human was the opportunity Fong was trying to exploit to improve the robot's navigation performance. So does this assessment answer our original design questions? It does answer the first question because the human can support interdependence with any aspect of this task except understanding when the robot is unsure. It also answers the second question in that the robot potentially needs support with interpretation. So how do we characterize requirements that meet this need? Looking at the interdependence analysis, there's a clear observability requirement, since the human will need to see the obstacle in order to interpret it. Being remote, the human is dependent on the robot to provide sensing in order to interpret. Fong provided this through a simple handheld interface. There is also an implied predictability requirement because the robot needed to notify the human when assistance was required. This may not have been obvious at first. Fong's intention was for the robot to navigate on its own and only ask for help when needed. The human was not supposed to watch the robot at all times, only to provide help when needed. This implies the robot is on its own to know when to ask for help, indicated by the red in the human column. This was accomplished by popping up a notification like the one shown here when assistance was needed. And last, there's also a directability requirement to allow the human's decision to alter or influence the robot's behavior. This was accomplished by some yes-no buttons on the interface. However, that's not enough to accomplish directability. It involves an algorithm on the robot that can incorporate that input into its decision cycle. The design implication here is that OPD requirements don't just affect the human interface, but can and often do also affect the design of the control algorithms. This is why the fundamental principle of coactive design is that interdependence should shape autonomy. All too often, automation decisions constrain potential support for interdependence. For more on this, check out my last video, Introducing Coactive Design. For our next example, we will use a fictitious Mars surface exploration mission. It involves multiple people and multiple robots, each with their own work to do. All parties can potentially help each other. As a model of the work, we'll consider using a tool to analyze a rock sample. It will involve going to a tool room, finding the tool, loading the tool, going to the area where the sample is, recognizing the sample, and analyzing the sample with the tool. This is probably an oversimplification of the work to be done, but it's a good starting point for doing some basic IA analysis. We will consider a team of 4 team members: an analyst robot like the rover shown here, a robot caddy that is mainly designed for lifting and carrying loads, a human astronaut in charge of operations, and a human geology specialist. We will consider one permutation in which the rover robot is the performer and the rest of the team is supporting. It would make sense to do another alternative with one of the humans as the performer, but we won't do that here for time's sake. It's probably not worth considering the caddy as the performer either, since it lacks most of the required capabilities. This demonstrates how all team permutations are not always necessary. So let's start by assessing the rover's capacity to do the task work. We see some uncertainty with both recognition and navigation. We also see the robot cannot lift the heavy tool itself, but it can contribute to carrying. Thus it's orange. Finally, we can see that although the robot can recognize its tools, it cannot recognize a particular sample it's trying to analyze. As we step through the team members, we can see the caddy can help with lifting the heavy tool, but nothing else. The operations astronaut can help with everything except identifying and analyzing the sample. And the geologist can help with everything except may be unaware of where the tools are kept. From this, we can see some important interdependencies and potential ways to support them. For example, there is a hard constraint that the geologist must assist in sample recognition. There is also a hard constraint to get help lifting the heavy tool, but anyone on the team can fill this role, and this provides more flexibility. Additionally, there are soft constraints. Though the robot can recognize the tool and navigate to the sample, it may occasionally have trouble and could benefit from assistance. Either human can provide this assistance. This does not mean they must provide it. It's a soft constraint, meaning it's optional. However, building in support for this potential interdependency means the team has additional flexibility and can make the team more resilient to problems it may encounter. Alright, now let's move on to a slightly more complex example from the DARPA Robotics Virtual Challenge. The DARPA Robotics Challenge was an international competition that involved lots of robots trying to perform disaster response tasks like driving, opening doors, turning valves, lifting hoses, walking over rubble, and climbing stairs. Our team used the Atlas humanoid robot from Boston Dynamics. The challenge started out in simulation with the Virtual Robotics Challenge. Here we will focus on a manipulation challenge, specifically a subtask of picking up a hose off a table. So let's start by modeling the joint work. The basic task description is to find the hose and pick it up. This can be broken down into locating the hose, walking up to the hose, grasping the hose, and lifting the hose. Pretty simple. This could be broken down even further by sensing the hose and recognizing that it's the hose that we want, specifying the footsteps to position the robot and executing those footsteps, positioning the hand for grasping and executing the grasp, and raising the hose for carrying. One observation is this is all the physical actions, and it isn't really talking much about the cognitive actions. We need to make sure we include those. Some of those include understanding the arm workspace, knowing where to stand for picking up the hose, knowing how to grasp the hose, verifying that the grasp is good, and potentially aborting the grasp if it's improper. Now let's enumerate the team. In the DRC, the robot works with the remote operator to accomplish the tasks. This means we need to consider two teaming alternatives: the robot performing the work with human assistance, and the human performing the work with robotic assistance. It may seem a little weird to consider the second option since the human is remote. They cannot physically do any of the work locally. However, one option is full teleoperation, in which the human drives each joint of the robot. In such a case, the human is doing all of the work and the robot is just performing torque control at the joint level, which you'll notice is not modeled in the work we are interested in. With the team alternatives enumerated, we then assess the potential for interdependence by assessing the performer's capacity to do the work and the supporter's capacity to assist the performer. We will return to this in a bit, but first let's consider some design questions that typically come up. It is common to want to automate parts of a given task, so let's say we wanted to automate the task of picking up the hose off the table, the entire task. What would be the impact of doing this? Give it a little thought. What considerations do you have? What options do you have? Engineers are typically optimists, and that's a good thing, but they also need to be grounded in reality. IA can help in answering this question about the impact of these common design questions. So let's see what IA tells us about this one. If we want to automate the entire task, we're basically saying we want to restrict our workflow to the robot performer column and ignore the rest of the alternatives. Right away, there's an issue. At this state in development, we had no ability to recognize the hose, as indicated by the red, which is a showstopper for automating this task. Surely our team could implement a hose recognition task, but that would require dedicating resources, and more than likely it would be yellow at best. If we didn't have the time to commit those resources, what other alternatives do we have? Let's say we wanted to automate the task after the hose has been recognized. Is that possible, and what is the impact of that design decision? The only red is on verification of the grasp and aborting if it's improper. If I am willing to accept that risk, then it is feasible to automate this portion of the work given the current state of development, but you do so at some risk. This is not the only risk. Knowing where to stand to pick up the hose and knowing how to grasp the hose are orange because of hard-coded constraints, meaning they could fail if the engineered assumptions do not match the real-world context. Additionally, choosing footstep and hand positions are yellow, indicating that the robot does not reliably place its appendages with high precision. This may seem odd for a robot unless you've spent a lot of time with physical robotic systems, in which case you're familiar with joint slop, backlash, and the host of dirty little robotic secrets. So yes, the hose task is automatable at this point, but with some caveats and some risk. I will pause here for a short takeaway lesson. Ben Franklin is cited as saying, if you fail to plan, you're planning to fail. In robotics, I would change that to be, if you don't plan to fail, you're failing to plan. You need to consider the fact that nothing's going to work perfectly, and you need to account for that risk. So back to our design questions. We know there's some risk, so how do we mitigate the risk in this task in particular? We just identified a bunch of different risks, which is one of the valuable features of IA. Can it also help us to understand how to mitigate them? Absolutely. One approach is to fix or improve the pieces that we wanted to automate, the yellows and the reds, in the performer column. But this is not the only option. The broad use of yellow is a way to force designers to remember that unless you can achieve 100% reliability, which is extremely rare, failure is always an option. However, another way to mitigate risk is to rely on a teammate for assistance. This is often the very purpose of teams, to make a group more resilient than any one individual would ever be. While there are some places where only the human can do the work, and other places where only the robot can do the work, there are a lot of places where both can contribute if designed to do so. Just considering human assistance for our example, we can use IA to identify the potential human-machine teaming options. If we include the second alternative with the human as the performer with robot assistance, there are even more options. Hopefully you're starting to see human-machine teaming not just as a nice-to-have feature, but as an essential approach to designing resilient and effective solutions that help mitigate risk. So let's continue with another design question. How do observability, predictability, and directability requirements turn into specification? This is important in order for the design to ground out in implementation. Unlike more common human factor design phrases like keep the human in the loop or maintain good situational awareness, I think you'll find talking in terms of interdependence more groundable. I'll provide a few examples of how some of the many requirements ground out in practice during the DRC. As an example, we will look at understanding the arm workspace. The Atlas robot has 6 degrees of freedom arms, and though they look like human arms, the range of motion is nothing like that of a human. While the robot has an inverse kinematic solver to provide this understanding, which is why it's green in the performer column, the human operator needs some help. Specifically, the operator needs assistance in understanding that arm space so that it can know where the valid positions and limitations are, and that needs to be made observable to them. It should also be predictable when the position cannot be achieved. Here we have phrased things in terms of observability and predictability, which we find translate nicely into engineering specification. There's still room for artistic interpretation about how to satisfy those requirements, but it should be clear when they are met and when they are not. This was our interpretation during the DRC about how to meet these requirements. We used virtual arms that allowed the operator to see where they were positioning the arm. The red hand indicates that the position is not reachable. We also use color to indicate when each joint approaches and reaches a joint limit. Knowledge of the end position is occasionally insufficient, so we provided a virtual preview so the human could predict the motion of the arm, not just the end position. This example appears to involve mostly interface work because we're looking at human observability requirements, but it also involved algorithmic changes. For example, the prediction seen here must accurately reflect what's going on in the underlying control algorithm. As another example, considering knowing where to stand to pick up a hose or manipulate things in general. Here, the robot can accurately perform this task, but cannot account for additional context such as obstacles. Therefore, the robot's position must be directable by the human. On the flip side, while the human can account for that context, it has difficulty understanding the constraints bounding the robot's motions. This shows that each have different weaknesses, which means that if they can work together effectively, they can help mitigate each other's weaknesses. Here is our Atlas robot standing in front of a valve instead of a hose, but the principle is still the same. You will see some engineered solutions as to where to stand to manipulate a particular valve. While the first option is all right, the second option actually collides with the corner. It would be nice if the robot could reliably avoid all obstacles, but if it cannot, the human needs a way to understand the constraints and adjust the robot's position. This interface allowed the human to have the robot virtually grasp the valve in order to understand proper placement and to stand and have a range of motion necessary to turn the valve completely. The last example is specifying footsteps. The robot cannot accurately assess the nuances of terrain features. The human, on the other hand, can assess those contextual nuances, but struggle with depth perception when operating remotely. Again, each have different weaknesses, neither is perfect, which again means they can benefit from working together. Here are several different ways the human and the robot can interact on footstep planning. The human may want to manually place individual footsteps, but it's more likely they'll rely on automated planning algorithms. However, the human may want to tweak those automated solutions, for example by adjusting the end stance, or maybe shifting individual footsteps within a plan that seem to be too risky. This interaction pattern is clearly not a distinct allocation of work from one to another. The human sets the goal, the automation makes an initial plan, the human can optionally adjust parts of that plan, and the automation can verify that those adjustments stay within acceptable control bounds. This interplay back and forth between the human and machine is much more like teamwork than task allocation. Those are just a few examples of how to ground out observability, predictability, and directability requirements into physical systems. There are obviously other ways to implement such solutions, but to be as effective, they need to support the same interdependence supported by these solutions. To summarize this introduction of interdependence analysis, I will highlight some of the key benefits of the approach. First, it models both the human and the machine. If you're going to design a human-machine system, any design approach needs to include both of those things. You'd be surprised how many approaches don't. Second, it can model multiple teammates, which allows you to scale your team. It also models the work context, which is important for understanding interdependence. It allows you to model both physical and cognitive work, which is important when considering how teams collaborate. Most uniquely, it models interdependencies between teammates. This is really the key to the whole approach. In particular, it models soft interdependencies. If you ignore these, you will have a much less effective team. It helps design for resilience by understanding risk, and it also helps design for flexibility by identifying alternative ways to accomplish the same work. Though we didn't cover it, it maps to implementation, and it also models potential workflows. But that's for next time. I hope you found this discussion on interdependence analysis useful, and hopefully you find the interdependence analysis table an effective tool in your arsenal as you design effective human-machine systems. Thank you.